Hello and welcome. Um, so far we have been talking about description of motion and kinematics in terms of Newton's laws. We were drawing free body diagrams. We were identifying forces, and then we set up Newton's um, equations, Newton's laws of motion, and then we were solving it. And last week we started to talk about the quantity that was different. We started to talk about something called work. And this week we'll continue along this direction, and we'll introduce a new quantity called energy. And we will see that this energy we defined, whether it's like mechanical energy in some cases or like total energy in other cases, it's we will see that it is conserved under all circumstances. And I think it is going to give us a new perspective. All right. So this is chapter 8 in your book, Conservation Energy. And here are your reading assignments, and this is your suggested problems. So before we can talk about energy, I want to start with this exercise. So previously, I introduced different kind of forces, right? Like I told you there were two kind of forces, like there were contact forces that were like acting when two objects were in contact, and there were like long-range forces like gravity that were acting at a distance. Now I want to introduce a different classification. But before do that, let's start with a simple exercise. And here I want to calculate. So imagine I have a particle like this, and for some, I don't know, maybe there's like an external force, who knows what happens. Somehow this particle moves from this point to this point, and it is under the influence of gravity the whole time. And I want to calculate the work done by gravity along this path, okay? And it is something like this, right? Work done by gravitational force is integral or line integral of force by gravity from 1 to 2. And watch this, I did not specify the path, and I will not specify the path, okay? This is like an arbitrary path so far. Now let's calculate this. So if I do this, it's like from 1 to 2, I know mg is equal to, okay, I can write mg like this, right? This is minus j direction, dotted into, I need to find an expression for dl2, but if I look at dl, I mean, maybe I can do it like this and show it in the next step. So here, so this is minus j, this is plus j, right? This is plus j, this is dl. So then this dot product can be just calculated from this angle, where this angle was like theta. So let me do that. And this is from 1 to 2, mg. But if I do this dot product here, you can see, let me zoom in. So this is j vector, this is dl. And if I do their dot product with cosine, I'm going to project this dl to this segment, but this segment is defined to be dy, right? This is y-axis, this is y position at any moment, and this is the infinitesimal, integral infinitesimal along this direction. Let me put that too. So then this one is, okay, there's minus, and there is dy, and there is, okay, maybe I can do it like this and you can see it better. It's like dl
cosine phi, but this dl cosine phi is dy, then I can do this like this. From integral limits now I can put y1 to y2 mg dy, okay, and I can take this integral, right? This is mgy from y1, okay, minus actually y1 to y2, and if I take this, this is, and if I put y2 minus y1 to be h like this, what I get is minus mgh. So what is interesting about this result is we, like I said, did not specify the path. We could easily consider a different path like this, and we could set up the same line integral and we would get the same result. So this only depends on height, or it only depends on initial and final configurations. So this result was not an accident, and I think you know this. Such results occur when we have conservative forces. So in the case of conservative force, the net work done does not depend on the path, but only on initial and final configurations. Okay? If this is not satisfied, we have non-conservative forces. Now, maybe I can follow this example and ask a couple of questions. Okay, let me see if I can see the chat box. Yes. So, for example, let's start with this question. What happens if I reverse the path in this figure? Rather than going from here to here, imagine I'm going from here to here. How would the work change? mgh, right? It would be plus mgh. It would just change the sign. Now, let's consider this example. Like, I'm going from like a point 1 to 2. So, and imagine the work done when I go from 1 to 2 along this path A is, I don't know, let's call it W. Then I can ask, what is the work done along the path B? And we are considering conservative force. What would the work done along path B be if this is W? That's also W, right? Good. Now, I want to change this picture a little bit. I want to keep A the same, so it's like W. But I want to reverse this path. Initially, it was like this. I want to reverse this path like this. Now, I want to ask, what is the work done along the path B? It's minus W, right? We just got this, yes. But now there's something interesting here. So if I start from 1, go to point 2, I can continue my journey along path B without any disturbance. And then I can come back to the same point. And now I look at the net work done by this conservative force, W in the first branch minus W in the second branch, the total path, total work is 0. Okay. This is also not an accident, and this is also independent of the path you choose. So for conservative forces, the net work done in a closed path is 0. And as a quick rule of thumb, if you like, the conservative forces generally only depend on position. If you see a force that depends on time or velocity, that's not a conservative force. Okay, so let's look at some examples of conservative forces. This is the table from the book. Here are examples, like we already seen that gravitational force is conservative. Elastic, like spring force, is conservative. Electric forces are conservative. I think we will not see electric forces at least in this semester. air resistance, and push or pull by a person, they're all non-conservative forces. Now, why do we call these conservative, right? There is actually a reason we call this conservative. And let me try to explain why we call it conservative. Let's think about this example. So imagine you are doing a work like this. You have like a mass at like say point y1, and you slowly raise this mass from this y1 to y2, which is a distance h above. Okay? And I want to ask myself, okay, I assume that I am moving it slowly, so what is the net work done by my hand? So I can, draw the free body diagram, and I can say, okay, if it's raised slowly, acceleration is 0, and this mg down should be balanced by equal and opposite force. Then it's like mg, like constant force, and then the distance h. So work done by hand is force times distance, mg times h, right? But when it is at this point, and imagine I release it, right? Imagine you just lift a box like a distance h, and then you release it. What happens? Without any assistance from an external agent, the box will start falling by itself. And when it comes to here, it's going to gain a kinetic energy, right? It's going to be fast. For example, if you put something here, it is going to have enough energy to smash this thing. If you put like a nail, you can probably put this nail in like a wood with this energy. So when you raise this towards the field, you actually store some kind of energy in this block. And this energy is there and it's conserved. And when you let it go, this energy just comes back. And that's why it's like a reversibility. There's like a sense of reversibility in this experiment, if you like. And that's the reason we call it conservative, okay? And for this, we say that the gravitational field or the gravitational potential energy is equal to mgh here, okay? And this is, I want to note that this is for this near the surface of Earth. We will see a more general situation later. So a couple of remarks quickly. So this definition, to be valid, we actually chose like a reference point. And what is physical actually is the change in potential energy rather than the potential energy itself. And the second remark is this potential energy is not a property of this block itself. It is actually a property of the system. And the system in this example is Earth plus the mass. You have to have both of them to be able to talk about the potential energy, this reversible quantity we just introduced. Okay, any questions? So let's generalize this a little bit. For any conservative force, whether it's like gravity or a spring force, we define the change in potential energy by minus the work done by that force. And if you set this up, it is like from initial configuration to final configuration F dot dl. Okay, this is only for conservative forces. For example, we did this for gravity and something like this, and we found that it was mgh. And you can actually do this for a spring like this, and you can find that it's 1/2 kx squared. I think we talked about this a little bit last week, so I assume you guys are comfortable, hopefully. So now I want to look at this equation, right? I wrote an expression for potential energy in terms of force. But actually there is like this relationship is interesting. And let me show you how. Like consider like a one-dimensional case. And in the one-dimensional case, you can translate this equation to something like this. U, the potential energy, is equal to minus the force dx. And I said the physical quantity is the change in potential energy. So there's like an overall constant, which I wrote here like C. And I want to like say, let me take derivative of both sides here and here. Right? I can do this. That's a legal operation. So this is like du dx on the left-hand side should be equal to minus. Now I have what? D over dx integral of f dx. Now I have, and okay, there is also the second one, which is constant, but we know it's 0, so I'm not writing it at all. Let's not bother about that. Now I look at this expression, I ask, what is the derivative of integral? Do we know this? So there's like a derivative of integral expression. Anybody know the result? If you take the derivative of integral, what do you get? F itself, right? Exactly. So derivative is kind of like a opposite of integral. Sometimes people call integral to be antiderivative, so they kind of cancel each other. So this is going to be minus f. Now I can clean up this intermediate step to show you what it is. So I want to put the minus here, and I want to put the f. So look what I get. So initially, I had the force, and I was defining the potential energy, but this expression is opposite. I have the potential energy. If I have the potential energy, I can find the force. So I can completely forget about force if I like, and I can describe my my system in terms of potential. And if at any point I need a force, I can use this expression, which is rather interesting. You can generalize this simple result to 3D, and it's like this. F as a vector is equal to minus w del x I hat minus the same thing in j direction and same thing in k direction. Here the important difference is that this del, this funny looking derivative, is partial derivative. And when you take a partial derivative of a quantity, say with respect to x, you assume everything else in that quantity is constant but x. So okay, now we have this. Let's we are in a position to introduce conservation of mechanical energy. So last week we introduced work energy principle, right? And we showed that the net work done on a system was equal to change in kinetic energy. So let's think about this network done. And like for the moment, let's assume that the only network done is done by the conservative forces, or there's only like this potential energy, right? I can write this expression then. The potential energy is network done by this conservative force with a minus, and this is equal to minus W net. So I can just put this here, and I can just write delta U rather than W net, and I can write everything in the same side. Then I will find something like this. Change in kinetic energy plus change in potential energy is 0. Or we sometimes say that change in total mechanical energy is 0, which is, you know, very nice, because if you calculate this kinetic energy plus potential energy at any moment, it's going to be conserved, and it's going to be the same at any other moment. And I can use this to solve problems like this, for example. Imagine you are dropping a rock from a height h. Initially, you have like potential energy u. Somewhere halfway, you have some potential energy, some kinetic energy, but their sum is the same as the magnitude of this guy. And at the end, the kinetic energy here is total potential energy here, and there is no potential energy here. A ball of mass m, starting from rest, falls a vertical distance h is equal to 55 centimeters before striking a vertical coil spring And then it compresses an amount y is equal to 15 centimeters, like in this figure. Determine the spring stiffness constant of the spring and assume the spring has negligible mass and ignore the air resistance. And measure all distances from the point where the ball first touches the uncompressed spring at y is equal to. So this is our reference point, okay? Maybe I can give you a couple of minutes to wake up with this problem. So the ball starts from here, falls on the spring, and after it touches on the spring, it starts compressing it, and it compresses all the way to here, and we know the distance. So the question is asking, what is the spring constant in this problem? So initially, okay, let's first look at the problem and try to understand what's going on. It is simple, I know, but let's just exercise. So initially, the ball is stationary, so it's not moving. It's held by some external agent, if you like, which is not shown. And all it has is like potential energy because it's at a height, okay? And it starts falling, and it starts converting this potential to kinetic energy. And when it reaches here, it has the kinetic energy. And it still has some potential energy, obviously, because there's still gravitational field. Now, because it has kinetic energy, it needs to stop. And to be able to stop, it's going to push the spring. But as it pushes the spring, it's going to convert this kinetic energy it has here to spring potential energy. And eventually here it's stationary. There's only spring kinetic energy, right? But since the problem is telling us to take the reference point to be here, there is also some potential energy difference that we have to take into account. So that's the description. So let's just identify point by point and just put this into an equation. First, y is equal to, let's call it y1, which is equal to h. So potential energy, so the problem is asking us to take reference point to be this here, measure all distances from the point where the ball first touches the uncompressed spring, y is equal to 0 at this point, okay? You can do that. U is equal to mgh, k is equal to 0, right? Now let's look at y is equal to 0. Here u is equal to 0, k is equal to 1/2 mv squared. But here E total is equal to mgh, should be conserved, and E total here should be the same, mgh. Then I can solve this for v squared is equal to mgh. Then, for example, v here is equal to square root of 2gh. Okay? So this was 1, 2, and now 3, y is equal to minus y. So now, okay, maybe I can write it like this. So this was like u gravitational, this is u gravitational, and here u spring was 0, here u spring was 0, right? Now u gravitational is equal to what? Minus mgy, and u spring is equal to 1/2 k y squared, and kinetic energy is 0. So E total is equal to 1/2 k y squared minus mgy. This should be conserved, and we know what this total is. It's equal to mgh, and I can solve this equation for k, right? From this, k is equal to mg
h plus y divided by y squared and 2. Is that correct? Let me put the numbers and see if I get what you got. 1585, and the unit is, okay, kilogram meter per second square meter divided by meter square, right? And this guy goes, so it's like kilogram per second square, or if we actually look like this, F is equal to kx, it's actually, you can see Newton per meter. They should be the same. Okay, then let's solve one more problem. So here there's like a simple pendulum shown in figure, and it consists of a small bob of mass m like this, and it's suspended by a massless cord of length L like this. And the bob is released without any push at t is equal to 0, where the cord makes an angle theta is equal to theta 0 to the vertical, like here, okay. Like theta 0 here. So A, describe the motion of the bob in terms of kinetic energy and potential energy, then determine the speed of the bob. B, as a functional position theta as it swings back and forth, and C, at the lowest point of the swing, and D, find the tension in the cord. So we will describe the motion, and we will find a velocity, an expression for velocity for a general theta, and for when it reaches here, and we will find the tension. Here is the starting point, and we know it is going to go back and forth. We know this is going to happen, but the problem is what's going to happen in terms of kinetic and potential energies. So when it's here, let's take this reference point like here as it is shown in the book. There's some height, and the velocity is 0. As it goes down, so this height and no velocity, then it's like a potential energy. As it goes down, this potential energy will be converted to kinetic energy. When it reaches the bottom, because this is the reference point, this potential energy is completely converted to kinetic energy. But at this point, it's not going to stop. It will keep moving, and it will go all the way up here until it stops. And when it stops, the kinetic energy here is completely converted to potential energy. And then this cycle repeats. So like we said, the potential energy is conserved. So it's like, let's call this y is equal to y naught. U is equal to mg. I need to write an expression for it here. This segment mgh. So when the cord comes here, its total length is L. So this whole length is L. So when the cord is here, is like this length is L times cosine theta 0. Then the difference is like your book wrote, L minus L cosine theta is your H here. Then I can write this. L, let's write it like this, cosine theta 0. And kinetic energy is 0. So let's imagine like a point y which is less than y naught, and it's like a general angle, let's suppose. And let's draw this. It goes from this point to, let's say, here, and something like theta. This point, u is equal to, I'll just replace theta with theta 0, theta naught with general theta. This is mgl 1 minus cosine theta, and kinetic energy is 1/2 mv squared. Now we use conservation of energy. So it is like 1/2 mv squared plus mgl 1 minus cosine theta is equal to the initial one, which is mgl 1 minus cosine theta naught. Then I think we can cancel these m's, and v is going to be, so 2gl, I think you can do the algebra. I can see where it's goes like cosine theta naught. So so the bob as a function of theta is back and forth, and at the lowest point of the swing, okay, so this is B, C at lowest point, theta is equal to what? Theta is equal to 0. Then cosine theta is equal to 1. Then V is equal to 2gl 1 minus cosine theta 0. Okay. And D, find the tension in the court. So this, I need your help. How do I find the tension in the court? Centripetal force. Yes, exactly. That's correct. And T is equal to mg. Okay, yes. So let's just now, go to our favorite, one of our favorite things, like writing free body diagrams and identifying forces, right? And this figure in your book already did that, but I can go through this. So there's like mg, and there is tension, which is shown with ft. Now this mg has two components. One is like this, right? The one is radial, the other one is tangential. So I'm interested in this guy and this guy. And I can see this bob is going to go through like circular path. So I can use the circular motion, right? So for circular motion, I know the radial force, whatever it is, it should be equal to centripetal force. So that's what I do. So Ft, its magnitude. So I wrote this guy. Now I need to write this guy, but this is equal to mg times cosine theta. Should be equal to centripetal force, which is mv squared over, and r is equal to L. Right? And I know the velocity for any theta, so I can put this. This is equal to m over L. And this is going to be v square is 2gl cosine theta minus cosine theta 0. Let's cancel else. And now I can carry this guy on this guy to find an expression for Ft. And Ft is equal to, let's write it like this, mg parenthesis, there's like 2 cosine theta and 1 more cosine theta is 3 cosine theta minus, there's only cosine theta 0, but there's 2 here, so it's like 2 cosine theta 0. Okay,
Now I want to generalize this notion we introduced. So far we introduced a total mechanical energy, like a kinetic energy plus potential energy, and potential energy was coming from conservative force. Now I want to include non-conservative forces as well. And for this, I will introduce conservation of total energy. And here's how I do it. And I say that total change in total energy could be like mechanical energy, like what we introduced so far already, kinetic energy and potential energy, and all the other energies. And the total change should be 0. And inside this all other energies, there could be some dissipated energy coming from friction. There could be some internal energy, like chemical energy or like some combustion. There could be some internal electrical energy, all the other things here I just put. And this statement is actually very powerful, right? We say that this total energy is conserved. So now let's see how this works in practice. And now I want to include the dissipative forces, like non-conservative forces, in my energy calculations. For this, I can just write down an expression for work done by friction, like this, right? Work done by friction, and friction force times dl. And I know friction force is always in the opposite direction of the motion, so it's like minus force friction times length of the path. And I said, okay, work energy principle was like this, right? Delta K is equal to W net. And inside this W net, there were two kinds of forces. There were like conservative forces doing work, and there were non-conservative forces doing work. And here is like spring and gravity, if you like, or this is the friction. And conservative work forces, we already calculated this, and we found that this was equal to minus delta U. Now I can put this guy on this side and combine it with delta K, and I say that delta K plus delta U, change in total mechanical energy, is equal to work done by non-conservative forces. Okay, in this case, it's like minus friction force times L. Here I want to remind you like an example from last week. Last week we had an example like this. Some force pushing a mass up on an inclined plane. And at that time, we identified all forces and we calculated the net work done on the block. And we used so-called work energy principle, right? Here, this is what we did last week. And some of you pointed out, how about potential energy? At the time, we didn't know about potential energy. Now we know potential energy, and this gives us an alternative way to solve this problem. So in this problem, there's block, there's gravitational energy, and as you push it, there'll be a potential energy, and there's like a non-conservative force, F of P here, and you can put all these things in here and then solve this problem in an alternative way, which I call approach 2. I encourage you to do so if you want to. But make sure you understand the differences here. If you use approach 1, do not add an additional potential energy because you already took it into account, or vice versa here, right? You just follow one or the other, not both. Now, in the beginning of the class, I told you that gravitational potential energy I wrote was valid for the surface of Earth. Now let's generalize it. And the way we generalize it is like this. We say that, is this the correct? Yes, okay. So the gravitational force follows inverse square law like this. At any point, if you have like a mass m, another mass m here, the gravitational attraction is like this. It's like gmm divided by r squared, and it's towards the center of the other mass, or like this, right? Maybe I can, should I calculate this? Maybe I can do this. Let's do this. I think it's sometimes useful to see it. Okay. Now this is equal to minus, let me take out all the constants, g, m. So integral from 1 to 2, 1 over r squared, r hat dotted into dl, right? So here is the geometry. At any point along your path, this is your r hat, and this is dl. Exactly what we did initially. If you take their dot product, you projected this dl to here, and this projection corresponds to the infinitesimal along the radial direction, which we call dr. So let's write this. Minus g m from r1 to r2, 1 over r squared dr. And I can take this integral. It is minus g m 1 over r, and this minus will cancel with this, and I will put r1 to r2, and this one will be equal to g m 1 over r2 minus 1 over r1, okay? So here is maybe an assignment for you. Like, maybe I can do it another time. Maybe I can do it today. It doesn't, I don't know. Let's see. So can you show that this expression goes to what we initially introduced, like mgh, as r1 and r2 go to, like, say, r earth? Like, show this goes to mgh. For distances around the Earth surface, what this means is r2, let's call it r earth plus h, and r1 is equal to r earth, and we assume that r earth is much, much larger than h. Can you show this? And let's continue with our initial program. Like we said that potential energy related to the conservative force was the minus of the work done by that force. So I'll take the minus of this. So here is my expression for gravitational potential energy. It's minus gmm, 1 over r2 minus 1 over r1. And we generally say that, okay, this is the change from position 1 to position 2. We say that at any point, at any general r, we say that it is proportional to this 1 over g m over r plus some constant. This is the expression for gravitational potential energy. Okay? And if you plot it, it's kind of like this. In the case of Earth, if you go to infinity, it goes to 0. As you go to the Earth's surface, it increases, and it's here somewhere it reaches to mgh, which you should show if you want to. And now we can use what we said. It was like kinetic energy plus potential energy at any moment is conserved. So 1/2 mv1 squared minus gmm over r1 at point 1, or like moment r1 is equal to 1/2 mv2 squared minus gmm over r2. And we can solve problems using this. The same way we used the mgh earlier. So here is there's like a special special V from this conservation form. So I want to ask, is there a speed? So because as you imagine objects moving around, if they go further away, their potential energy decreases, and as they go this, because like this 1/r goes to 0, and as they go to Earth's surface, their potential energy is converted to kinetic energy, and their velocity increases. And I ask myself, if I start with some velocity v, as I go up, this v will decrease, but potential energy will increase. But is there a velocity that this v will keep going on and on and on without any return, so that this initial particle will go to infinity? And that's called the escape velocity. To calculate that, we said here R2 is equal to infinity because it goes to infinity. And to find the minimum value of this V, we said at the infinity, we assume that it's like stationary. And then we solve this equation for V, something like this, 1/2 mv, this escape velocity squared is equal to gmm over Re. Re is the Earth radius. And if you solve it, you find something like that. This V escape is like this. If you put the numbers, it's like 1.12 times 10 to 4 meter per second. This is the escape velocity of Earth, which is like a very big number. Okay, so I want to define power. So power is defined as work done in time. So when we talk about things in unit time, what we did as always, first introduce the average and then introduce instantaneous, right? So we introduced the average power like this. Power is work done by total time. And if you look at the unit, it's like joules per second, and we call this watt. Okay. And for example, if you hear about horsepower, which is the natural units in like more like mechanical vehicles, it's equal to 746 watt. And this was, I think, calculated by Watt himself. Or for 1 kilowatt, you have 1 1/3 horsepower, something like this. So this is the unit. Now from this average power, we introduce instantaneous power as the derivative. Exactly what we did for all the physical quantities so far, right? Since work involves some sort of energy transfer, we saw that, right? Work is like energy, and when you do work, you transfer energy from the worker to the workee, if you like. And it is like this: power is equal to dE dt. And if you manipulate this, P is equal to dV dt, you can take dt and write work as like F dot dL, or d work, actually, this is d work. And if you take the derivative to here, it's like F dot dL dt, but this guy is equal to velocity vector, so power is equal to F dot V. So this is the scalar product of force vector with velocity vector. And we are assuming constant force for this expression, but you can derive a similar expression for varying force, which will be integral. So what is important for mechanical engines is the efficiency of engines. And the efficiency of engine is defined as output power divided by input power. And input power is whatever you put is calculated, right? You put some input power and you get some output. Could be like some gas, some chemical, total energy per time. It's your input, and then you watch how much you get. And this is always less than 1 because there is no perfect engine. And as an example, for like average car, this efficiency is about 15%, which means 80% of total input energy is wasted, which is rather interesting. Okay. So finally, I want to talk about this potential energy a little bit more. So what did we do? We introduced energy, and based on what we introduced so far, it seems like energy is like a more fundamental quantity. And actually we sometimes don't need force at all. We can just work through energy, and sometimes problems are easier. And here's an example. We can look at this potential energy diagram. Like suppose somebody give you a potential energy diagram like this, okay? Normally, if it was a spring, it was like this, right? But here it's a little bit more complicated, and I want to describe the motion. And if we have this, I think we don't need anything else. This is the beauty of this approach. And potential energy basically tells about all kinematic motion. We can describe anything we want, and let's see how we do this. So we need to determine the total energy, or total energy should be given. So, and we draw this total energy with these horizontal lines, right? If I draw this line, that means total energy is E naught, or this line, total energy is like this, or it could be a lot, but it could be even higher. And I want to describe the motion by this, right? By this total energy and potential energy diagram. Let's start with E naught. So if my total energy is this and my particle is here, can it go up or down? For it to go up or down, it needs to have an energy to convert, right? Because going up requires additional potential energy, but it should come from somewhere, but we don't have it. So when it is here, the particle will stay stationary like this. Now let's imagine our energy is like here, like we are looking at the different system now. And I want to describe the motion of this particle. If it's starting here, it is the maximum potential energy, and it's going to roll down the hill like this, converting this potential energy to kinetic energy. And any moment here is your distance from this initial position is going to be your kinetic energy. And when you're at the bottom, your potential energy is fully converted to kinetic energy, and you will go up and you will continue doing this motion. So if you are here, for example, there's like a little bit of different situation. Now, for this side, I can talk about exactly the same motion, but the amplitude is a little bit bigger, like this. But this is not the only configuration, right? I could also have something like this, because total energy satisfies both of them. And finally, if it's like E3, you can see the particle, if it starts here, can roll over the hill and again, and then go to infinity. So I encourage you to go through this. And for example, you can make a table like this. Make a table and try to describe the motion like we did for E is equal to E naught, E is equal to E1, and so on and so forth, okay? And you'll see this will actually be helpful in a lot of cases. You can easily look at the potential energy and understand what's going on. You don't have to just sit down and write all these equations in some cases. So here's the problem. Consider the track shown in this figure, like this. And the section AB is 1 quadrant of a circle of radius 2 meters, this part. This is a quarter of a circle, like this, if you like. Okay? It's hard to draw, but like this, maybe. 1 quadrant of circle. And it is frictionless, good. But B to C is a horizontal span of 3 meters long with a coefficient of kinetic friction mu k 0.25. From here to here, it's like given, and it's like friction, like there's some friction. The section CD here, under the spring, is magically frictionless. And a block of mass 1 kilogram is released from rest at A here. After sliding on the track, it compresses the spring by about 0.2 meters. determine the velocity of the block at point B here. B, the thermal energy produced as the block slides from B to C, how much thermal energy is produced from here to here. And C, the velocity of the block at point C here, what is V? And D, the stiffness constant K of the spring. These are a lot of things to ask for, but I think we can do all of them. A. So what is the velocity of block when it reaches B? When it is here, okay, maybe it's hard to, I think this figure is not nice. It doesn't look like a full quadrant to me, but that's fine. So at A, I have potential energy, which is mg, but H is equal to R. And kinetic energy is equal to 0. Now I go at B, I have potential energy is equal to 0. Kinetic energy, let's call it 1/2 mv squared. And from conservation of energy, I have mgr should be equal to 1/2 mv squared. Cancel m's. V is equal to 2gr inside the square root. And if we put the numbers, let me write 6.2 meter per second for you to compare. And I think I should compare with you because I didn't get the wrong result. So I hope that's correct. This is meter per second. B, the thermal energy produced as the block slides from B to C. Okay, so I need to, okay, now the block is here. Maybe I don't need that line anymore. But I need the block at B. And there is like mg, there's like normal force. And I know normal force is equal to mg, and friction force is equal to mu k times normal force, which is equal to mu k times mg, right? And so work done by friction is equal to minus, okay, I should put F here, minus friction force times, let's call this D. D, and should I calculate this? What is the question asking? Let me go back. Calculate the thermal energy produced as the block side. Okay, then, okay, this is the thermal energy, right? If the friction is this will be converted to thermal energy because energy does not disappear. This friction goes to thermal energy. And for this, I need to maybe have one more step. It's minus mu k m g d. Let's put the numbers. 0. So this is equal to 7.35 joules. Let me know if it's not right. C, velocity of the block at point C. Okay. So E is equal to, okay, maybe I can use this because mgh at B, and E should be conserved, so it is equal to mgh minus mu k mgd. This is at C. Then this should be a fully kinetic energy, 1/2 mv squared is equal to mgh minus mu k mgd. And the question is asking us to find the velocity of the bug at point C. We can do that. Cancel m's. V is equal to 2 g h minus mu k times d. Is that correct? Hopefully it is. I'll put the numbers. This is 4.9 meter per second. Is that correct? Hopefully. Please check these numbers and let me know if they're wrong. I can go back and fix it. D and stiffness constant. Okay. So now when it is compressed, E is equal to spring, let's say 1/2 k x squared, but this should be equal to mgh minus mu k mgd. Then spring constant should be, so mgh minus mu k d divided by x squared. There's like a 2 in front, and that's it, right? I was going to take square root, but there's no square root. So it's just k. And let's calculate this. It's equal to 612. I'll call it Newton per meter because it's easier to write. Why there is no centripetal at B? I don't know. Maybe did I mess anything up? Maybe you can explain and I can take centripetal in B. Is there like, so the question is, so this is like a circular motion, right? This is like this from here, okay. From here to here is a circular motion, and we know there is like a centripetal force related to circular motion. And do we have to take this centripetal force into account in some way, or did I miss thinking about that? You said part B. Let's go back to part B. Okay. Maybe you can tell me what I should do and I'll follow. I think B is where circle ends, so there's no centripetal force. So, okay, I want to get like a more clear question. What is the question? Let's think about that. So there is like some objection about centripetal force. I want to see the statement of the problem here so that we can talk about it. Did I mess up something in this calculation? I agree with Toprak. Okay. So if it wasn't the previous point, there may be. But I don't understand the problem. So what is the problem with centripetal force? What did I mess up? I think at B, F normal is bigger than mg, but there is no friction until B, so it doesn't change. Okay, there is like a fair point. So I think at B, F normal is bigger than mg, yes, but there is no friction until B, so it's not going to change the result. How about that? In the point B, is there any effect of a centripetal force on the object? That's exactly what we are discussing. So any resolution? So should I do anything different? If you suggest, I will do it. What's your suggestion? What should I do? So I think I can first clarify the question because nobody said anything about the question. So we calculate the normal force by saying, okay, let's see where we did this. We calculate the normal force like this, right? We said that normal force is equal to mg, and we plug this into the friction because friction is mu k times normal force, and from this friction we calculate the work by friction. Now the question is, do we have to modify this result due to this circular motion? So here is my point. So let's call this B, okay? Maybe here's B. And it is true that there is like a circular motion until you reach B. And this circular motion should have like a centripetal force. Let's call this Fr, right? And there should be like some mg. And I think I challenge you to calculate this F centripetal at any point along this curved path. I think it's not hard. We can do it, but I think there's no point for now. But now you are here. As soon as you hit here, of course, there's no friction here. I think it would be a nice question to solve. If they said there is friction here, we would have to calculate this Fr, and then we would have to subtract this energy from friction to calculate the total energy when the mass reaches here. But the problem is actually making it easier for us because there is no friction here. Now let's look at here, the particle. Okay, I forget about this part. And now I focus on here. Particle is here, and it has some velocity, and it has some weight. I don't know, maybe mg, and it has some normal force, F normal. And now the friction is starting to take place, right? And there is no more circular motion. It's like it was in the past. We forget about past, right? And we do what we do for linear motion, and that's what I did. I think it's a nice exercise. So I would say for if you want to do this exercise, go ahead and do it this way. Like, let's remove the friction here and put the friction here. And let's see how this centripetal force is taken into account in that case, okay? But in this case, the problem is making it easy for us by not having any friction here. So when the object moves from B, does Fn become equal to mg? But before, yes, exactly. As soon as it reaches B, there is like a discontinuity, right? There's like a discontinuity of path, if you like. The path is curved until B, and there's like a circular motion, and that circular motion discontinues at B because the path changes. Here is you have circle, here is you have linear. You have to transition from the circular motion to linear motion. But here its normal force is equal to mg. So that's why we didn't have to deal with this. I think, let me repeat this point. I think that's a nice thing to point out. Like you said, so there's like a change after this point. Up until this point, this normal force is actually bigger than mg because of circular motion. But when you hit here, there's no more circular motion, so normal force is equal to mg. I actually like this discussion. Thank you for asking this question. Yes, you can ask Turkish if you want to. I like this question, and I think it was very useful. So if it's like this, right? And let's put this like this, the mass. So here is mg. Here, okay, this is towards the center. Here is F normal. And the question is if F normal is bigger than mg. And my question is maybe it is not. My answer is maybe it is not. So here is, I don't know, some theta. I think this is going to be mg cosine theta. This one will be mg sine theta. I think that's what we did. And F normal minus mg cosine theta is equal to m v squared over, okay, r. I think I want to take this back. F normal is not necessarily bigger than mg, right? Because of this cosine. There's actually a cosine factor, so F normal may or may not be bigger. And now can I find an expression for V? I think this is not hard. I can do this maybe next time. Okay, I'll remove this. So maybe I can try to do this next time. But what happens is like this, okay. So I want to take back what I said. It could be right or wrong, but it actually doesn't matter. So there is some force, and this F normal is changing as you go from this circular path to this linear path. And your question is, if there's like a jump in Fn, there's like a change, a sudden change in the value of Fn, where does it go? I think maybe there is no sudden change in Fn. And my hunch, I don't know because I didn't do the calculation, but my hunch is that actually Fn continuously changes from some circular motion value to mg. And if I were to guess, I would say it's going to be something like this. So here, normal force is 0, right? There is no normal force. I would say if you plot, so F normal magnitude as a function of, I don't know, theta, and theta is this angle from 0 to pi over 2. I think initially it is 0, and at the end, I think it's going to reach maybe linearly, maybe not, but it's going to reach value mg, and after here, it's going to continue constantly. So there's no gap, okay? I actually like this question too. That's also a very useful thing to think about. Does this make sense? So this, if linear, I'm not sure, maybe it is like this, or maybe it is like this. We need to do this calculation to be able to tell an exact statement for this, okay? The person who wrote this question probably thought about the complication here, and he was like, okay, this is a little bit beyond, so let's not put friction here. That's why they probably did it this way. So your graph says Fn is equal to mg. So my graph says Fn is not always so. This is, Fn is changing as a function of, like, this is, okay. This is Fn. So this is the value of Fn. For example, Fn here is 0, right? There's no normal force here. There can't be a normal force. Whereas a little below, it's going to increase. A little below, it's going to increase. So as you go from this top point to here, this normal force will continuously increase. That I know, right? That's for sure. But we don't know how it increases because, you know, I don't want to deal with this equation now. Maybe it's simple to do, but I didn't do it. So maybe it's increasing like this. Maybe it's increasing like this. Maybe it's increasing like this, but it doesn't matter. It starts at 0, and when it reaches point B, it becomes mg. That I know for sure because it has to go continuously. So there is no, yes, exactly. That's a good point. It reaches mg at this point, so there is no centripetal. Yes, thank you for pointing this out too. That's also right thing to point out. Yes. So Fn becomes mg here, and then there is no, yeah, that's correct. I didn't read the rest of your comment. Thank you. Thanks everyone for coming. And I will see you guys tomorrow.